Okay, so this unit, we're just going to basically be focusing on gases and their behavior, and just kind of how there's different variables of gases that we can measure and how they kind of all relate, and just kind of how you see this in your everyday life. So we've already talked about the states of matter at the very beginning of the class. We know we have solid, liquid, and gases. So like I said, we're just really focusing on these gases. So that's what we're kind of make sure we understand. Remember, gases have high kinetic energy because we know that because they're moving around really fast, they're really spread out, but they have very weak or virtually no intermolecular forces. So those attractive forces that we've talked about that kind of keep our molecules together, like dipole or hydrogen bonds, right? There's virtually none of those for a gas. There's nothing keeping those individual molecules together. They're free to roam about the space kind of at will. One thing to just kind of refresh our memory on, this is since it's been a while, kinetic energy and temperature. Okay, so temperature is just a measure of kinetic energy. Okay, so if we think, if we have a solid, right? If we have a solid, it starts out all kind of packed in tightly, right? If we add heat, which makes our temperature go up, what we're really doing is giving energy to those molecules. So now they're going to start moving around very quickly. They're going to start spreading out. Okay, so not only has our temperature gone up, but also our kinetic energy has gone up. And then I could do the same thing. If I went backwards and I removed heat or removed that energy, okay, then my particles are going to kind of go back to being all nice, packed up, real tight together. Okay. We're going to come back to properties a different day next week. So just a few of the things that you kind of collected some data on yesterday were the gas laws. And these gas laws kind of help answer this question, why, for a lot of things. So like if you play basketball or soccer or any kind of sport where you might leave your ball outside overnight and it's kind of chilly, if you go get it the next day, you might notice that it's gone a little bit flat, right? So it seems like the air left. Why do spray cans explode when you throw them in the fire? If I squeeze a balloon, why does it eventually pop? Okay, so some of these answers you probably know already, or you could at least guess, like, oh, I throw it in the fire, it explodes because it gets hot, right? So that's true. So you kind of already have this introduction to these gas laws, even though you may not have known their names or really known what it was. So this is kind of where your notes pick up. There's just some important variables that we can measure. These were the variables that you were looking at yesterday in the simulation. So we have our volume, we have pressure, and we have temperature. So we just need to make sure we know what those terms mean. So volume we know is really just like the amount of space something takes up. Pressure is really like the force acting on a surface. So if you think about it, like if you watch any of those medical dramas where somebody's bleeding and they say, put pressure on it, and somebody presses down, right, on whatever wound there is. So you're applying pressure. Okay, what you're really doing is you're putting a force. You're pressing down, you're applying a force on the surface. That's all that gas particles do. If you think about like a balloon, okay, if I have all these little particles, every now and then, right, they're bouncing around on the edge of the container, the edge of this balloon. And what's happening is they're applying a force or a pressure to the outside of this balloon, and that's what's making the balloon expand, right? As you put more particles in, as you're blowing more air in, you're increasing the amount of gas inside the balloon. The pressure inside the balloon increases. So it's more and more force that's pushing that balloon bigger and bigger. Okay, and we just talked about temperature is just how much kinetic energy an object has. So in your notes, you're kind of just filling in the chart, basically. So Boyle's law, when we're talking about Boyle's law, we're talking about pressure and volume. Okay, and they are, it's really inversely, is really more correct to say they're inversely related. Okay, so what that means is that they're just opposite. If one goes up, like if I think about if my pressure, if I'm increasing my pressure, okay, what's going to happen is my volume is going to go down. Okay, if I think about like a container with a lid or something, if I'm closing the lid down, okay, or like if you're squeezing a bottle, right? You've all probably seen where you jump on a water bottle and it spits the top off, right? So I'm decreasing that volume, the size of the bottle, the size of the container, that's increasing my pressure. Okay, that's what makes that lid pop off. So they're just opposite. One goes down, the other is going to go up. Okay, we're not measuring temperature here, so we have our constant temperature, and then we have this equation that we were going to use later on to kind of calculate some problems. So we have our Boyle's law equation right here. And then in your notes, I think you can see we have a graph for when we have something that's inversely related, and basically it's just kind of showing how those variables are related to each other. Okay, so I think that's already filled in your notes. Okay. Then we have Charles's law. We're just talking about temperature and volume. Our constant is pressure. We have our nice equation down here. And then since they're directly related, what that means is if temperature is going up, volume's going up. If temperature is going down, volume's going down. Okay, so what we have is this type of graph. It's a direct graph. They're directly related or proportional. So as my temperature is going up, so is my volume, okay, and vice versa. Gay-Lussac's, so like pressure and temperature, they're directly related. So again, that means if one goes up, the other is going up. If one goes down, the other is going down. Okay, so this would be like why if you throw a can in the fire, it's gonna explode, right? Well, my temperature is going up in the fire, so that means the pressure inside that can is going to start building, and eventually it's going to explode. Okay, and then I forgot to tell you Charles's law. This is why that basketball that started out all nice and right, b-ball, all nice and pumped up, ready to practice. On a cold night, you kind of go back out and it might be a little bit deflated, okay, because my temperature has gone down, and so the actual space that volume, that gas takes up, the actual volume, the space of it has decreased. So that means that the ball is just basically gets smaller. Okay. So this is kind of down, I think, on the next page where we're going to do the calculations. What we've done is we have what we call the combined gas law. We've just kind of combined all these equations together. So all these individuals were studying all these different variables and how they're related together. And then they figured out, oh, well, we can actually push all of them together. We still have all of our individual formulas, but we kind of push them all together to make this combined gas law. So nothing changes about how they're related. Basically, we can even, when we're doing some calculations, if we don't need a variable, we can basically ignore it. So nothing's really changing about the actual formulas. We just kind of push them together. Okay, one thing to know is that whenever we're plugging in our numbers, we want to convert our Celsius, our degrees Celsius into Kelvin. We're going to do that by just adding this 273.15. Okay, so let's do some practice. So remember, I have my combined gas law. T2. Okay, and it says 2 liters of a gas is collected at 25 degrees Celsius and 0.9 ATM. Okay, so this is all my first bit of data. So this is going all in the P1. So my pressure, this is my ATM, 0.98. Okay, my volume is 2 liters. Okay, and then my temperature is this 25 degrees Celsius. But remember, I have to change it to Kelvin. So I'm just going to add that 273.15. Okay, so I end up with 298.15. So now let's come on over here with my P2, V2, T2. So this says STP. This is kind of a shortcut for chemistry. So STP basically stands for standard temperature and pressure. This is like the normal pressure. It's 1 ATM and 273.15. It's kind of like sea level. What's the pressure at sea level? 1 ATM. Okay, what's the pressure or what's the average temperature? Okay, it's about like room. This is like room temperature, basically. So when I plug this in, okay, my pressure for P2 is just a 1. My volume, that's what I'm looking for. It asks me, what is my volume? Well, I don't really know. That's going to be my variable. Then my temperature, it already gives me to it in Kelvin, so I can just plug that in. Okay, so in order to solve for this V2 here, what we can do is we can just cross multiply. Okay, so if I cross here, I'm going to get 0.98 times 2 times 273.15. Okay, when I cross here, I get 298.15 times 1 times my V2, my unknown that I'm looking for. So if I multiply all that out together, 0.98 on my left side, end up with, I'll have to kind of come over here, 535.4. And then on my right side, it's just 298.15 times my V2. And if I need to get my V2 by itself, I can just divide by 298.15. So those cancel out. And I can just type in my computer or my calculator. So you get about 1.8. Okay, and this is volume, so our units are going to be liters. So this is my final answer for that problem. Okay, let's look at another one. This one's a little bit simpler. Okay, so I still have my my ideal gas law here. Okay, so I'm just going to kind of look at my question. So it says if 2 liters of a gas is 740 millimeters mercury. So that's my pressure. Okay, so this is what I'm starting out with. So I'm just going to plug that in to 740. And then since I don't have a temperature, basically we're just going to kind of ignore this bottom part of this equation. So I'm really just looking at the top. Okay, so V2, what is the volume? That's what I don't know. At 760, that's my pressure, right? So now I can just solve by dividing my 760. That's going to get my V2 by itself. So I'll do 2 times 740 divided by 760. And you end up with about 1.9 as my volume. And again, this is volume, so this is going to be liters. Okay, so what I'd like, I'm going to work these out for you just so you can see some more examples, but I'd like for you to pause here, at least try these by yourself, at least get as far as you can setting up, and then press play and watch me work out the last little bit, and I'll just kind of work through them pretty pretty quick here. So I'm just going to write my combined gas law. 4.4 liters of gas, 50 degrees Celsius. So my volume, so what I don't have in this one is pressure, so I'm just going to kind of ignore it. So 4.4 over, and remember, anytime we have temperature, we have to add that 273. So we end up with, it's 273. I typed wrong, 323.15. Okay, my second volume is what I'm looking for. What is the volume when I cool it down to 25? So again, I have to add that 273.15. I get 298.15. So I can solve this by cross multiplying. So 4.4 times 298 equals 323.15 times my volume that I don't know. And then I can divide by the 323. What I do to one side, I have to do to both. Those will cross out. Once I type in 4.4 times 298.15, I'm going to divide that by the 323, end up with 4.06. And again, this is volume, so it's going to be liters. Okay, if you don't get this answer, it might be because you didn't change your temperatures here to Kelvin. Okay, so just don't forget to do that. All right, last one. Let's write our formula. If you didn't pause at the last one, you want to try this one by yourself. That would be a great idea. So this is a constant volume, has a pressure of 0.35 and a temperature of 50. So constant volume, that means I'm not messing with my volume. So I'm just going to kind of scribble that out in my problem. So it says a pressure of 0.350, and then I need my temperature. Remember, I have to add 273.15. So that gives me that 323.15. Okay, then it asks me what is the pressure. So that's what I'm looking for. That's like my X value. Okay, and I want to know when the temperature's doubled. So I'm going to double this Kelvin value. I'm not going to double the Celsius value. So 323.15, if that's doubled, it's 646.3. Okay, so I just multiplied this 323 by 2, basically. And then now we can solve by cross multiplying. So 0.350 times 646.3 equals 323.15 times P2. Okay, I can divide by the 323. Okay, those will cross out. So my P2 is going to equal the 0.35 times 646 divided by 323. And it comes out to be about 0.7. Okay, and remember that's pressure, so I'm going to use my units for my pressure earlier, which was ATM. So if you're ever unsure about the units, you can always just go back and look at whatever they were at the beginning. That's the same units that you're going to have now. Okay, so hopefully these last two weren't too bad for you. If you need some more practice, or if you need me to work through a few more with you, I don't mind. Just email me, and we can do or come to the office hours or the Google